Welcome to the course of Intelligent Product Design. We are now in the world of actuators. We have earlier talked about the sensors, and now in this particular two lectures we will be talking about the actuators. Now, actuators are also similar to sensors in a sense that both actuators and sensors. So, there is a common group actuators and sensors. In one sense they are similar. What is it? That they are both transducer. And what is a transducer? The transducer survives on energy conversion. Okay? So, we are going to look at some of the useful energy conversions in this lecture, where we can using which we can do the actuator design. So, I will talk about why at all the energy conversion is needed and energy conversion specifically in actuators. Then I will talk about electro-hydraulic actuators, electromagnetic actuators, etc. Now, the domain in which we are in the real world is the stop world, that is where the physical process involving a combination of mechanical, fluid, thermal, chemical, electrical components and subsystems, they work. And this world is continuously probed by the sensors, but the sensors need very little energy. Whatever sensors you have seen, they can all be run possibly in the level of milliwatt kind of power. So, they need little energy. So, they are in the low power domain. However, once the sensor senses whatever is happening in this physical domain, which is high power, it actually sends the signals for the signal processing and different softwares. All these things are today mostly embedded in microprocessors and microcontrollers. We will talk about it in the future lectures. Now, so this is also in the low power domain. So, both the sensor and the processor are low power domain, but whatever the decision comes from this processor that some actuator is required for some correcting activity on the physical world or to make some adaptive changes, then you have to jump up to these actuators and you have to invariably do some energy conversion, some power modulation, and then the actuator is going to work, interact with the physical world. So, even though both sensors and the actuators are on the based on the energy transduction principle, while sensors work in the low power domain, actuators work in the high power domain. That is an important point we have to keep in our mind. Now, let us look into further that a fully mechanical system is possible very rarely. For example, if you have to store energy in a fully mechanical system, you can store it in terms of springs as potential energy or flywheels and kinetic energy and extract as required. You will see some toys are based on such a system. So, that means, if you have to design a system which will remain in the real world and have a energy conversion or energy storage in the real world and then drive the actuators in the real world, that possibility is something which is generally avoided because of these following reasons, that the closed loop system development is generally not possible. There are some exceptions. One exception is the Watt's governor system. It is based on a fully physical high power domain of a sort of a control system. So, Watt's governor. So, governors are such a system where it is not required to go to a low power and then high power, but in general this is not possible. Again, another problem why it is not possible is because energy, mechanical energy I should say here, that mechanical energy, not just energy in general, but mechanical energy could not be transferred to a long distance, loss is quite high. Okay. However, electrical energy could be transferred up to a longer distance. So, if I have to take some corrective action in a longer distance, then electrical energy is the best. Suppose I am driving something remotely, then electrical energy is the best option. And of course, mechanical energy direct application will not be green, clean and economic, whereas in the electrical energy it is possible. So, all these factors drive us to go away from a fully mechanical system to an electromechanical system. Like you can see here that some of the earlier designs of a manual transmission component in vehicle, which is a fully mechanical system. It has a flywheel, it has clutch and gears, all these things you can see that it is present in the systems in a way that you do not need any electromechanical part, but this is heavier, not so clean, have lot of noises and energy losses in the process. And if you look at even an electric motor, you would see that there is a hydraulic torque converter, automatic transmission and there are cutways. So, this is a system which is electromechanical in nature. Now, energy conversion in actuators takes place in generally the 6 different ways. The first and foremost is of course electromagnetic like the motors, and then electro-pneumatic and electro-hydraulic system, and then electrostatic MEMS based system, something like this that I have shown you here, piezoelectric system, and so these are smart systems, last 3. These are based on the smart material that we have discussed in the last class while talking about the sensors. So, piezoelectric such as PVDF, magnetostrictive such as terphenol D and phase change related such as nitinol. These are all smart material based system, smart material. Okay. Now, let us just have a comparison of different types of actuators in terms of 2 important things. One is how much of maximum stroke it can generate, and another is how much of maximum output force it can generate in Newton for the force and in meter for the stroke. So, what we can see here is that if you talk of a large force, something like a human muscle can generate, then or even much more than that, then you have to inevitably come to systems which are like pneumatic, hydraulic and electromagnetic and all these things. This is a large force you can see here. If you think of a large displacement, not large, very large force, then you have options like shape memory, electroactive polymers. And if you are thinking of moderate force level, not moderate deflection, then you have these piezoelectric materials with you. Okay. If you want to talk about a large force level, then you have magnetostrictive material as one of the best choices. And if you are talking about low force and low stroke, but high precision, then we have to go for MEMS based drives. Now, this is the stroke versus force comparison. Let us look into another comparison, which is weight versus frequency. If we want to go for a system where weight penalty is not of our concern, then we can go for hydraulic or pneumatic systems, because they are much heavier in nature. If you want to go for low weight system, then I think electroactive polymer is a good choice, even SMA also is a good choice. If you want to go for high frequency, moderate frequency level is MEMS, but high frequency you have to go for piezoelectrics, because their bandwidth we have seen in the last class is really very high. And that is also true for some of the electrostatic and magnetostrictive systems. So, that is another point, while choosing the actuators, these are the two concerns that you will always find, that what is the force versus what is the kind of weight of the system and what is the stroke level. So, force and the stroke. So, let us try to write it down here, that the two important points that we have to always take care of are, one is the force versus stroke, force stroke, and another one is weight versus frequency. Okay. Of course, you can have situations where you will be choosing the actuators based on force weight, how much of force I am getting versus how much of weight I am getting, or the other one, that is how much of stroke I am getting versus how much of weight. And in this case also, like frequency and weight, we generally also come across another kind of a chart, which is force versus frequency. How much of force I am getting, whether that force is static in nature or dynamic in nature, low frequency or high frequency. So, all these type of 5 charts similar to the ASB charts that we have seen are required for choosing a proper actuator for our intelligent product design. I will give you some example of actuators now. One example is the EH, electro-hydraulic actuator. So, how it would work is that the power of the hydraulic supply, the fluid pressure, the thrust, that will come from here. Okay. So, this is how it is coming, and then here you have something which is called a flow control valve, a very important thing. Okay. The flow control allows the power to come into the main system, and let us say if you allow the flow to come, who decides that? That is decided by a servo controller. So, servo controller, what does it know? It only knows what is the demand position. If the demand position is such that you need to have force, then servo controller will open up the flow control valve and hydraulic power supply will come immediately, and that will drive a linear actuator, and that linear actuator will work on the load of the system. Again, there will be sensors. These are the displacement transducers. They would sense that whether a given load is deformed by a particular level or not. If not, then it will send that signal to the servo controller, and servo controller will further allow. And if the displacement is reached, then this flow valve, flow control valve will be stopped. So, the fluid, the hydraulic power would not come, and the linear actuator will not work anymore. So, that is the kind of a design of an electro-hydraulic actuator, the basic network in which it would work on. And this is a piston movement that can be controlled, the force movement using this type of a network of a system. Now, electro-hydraulic actuator, then the flow path can be visualized. This is a real life electro-hydraulic actuator system. The flow path can be motor like the servo motors, and then the pump, spool valve or a poppet valve, then that goes to accumulator, pressure release system, and loading path or return path. So, these are the things that you need to design in order to design an electro-hydraulic actuator. I will show you one typical example of such actuators in a helicopter. In a helicopter, you generally see you have one main rotor and you have a tail rotor. So, this is a main rotor, this is a main rotor, and this is a tail rotor. Okay. So, each one of them will be generally operated by electro-hydraulic actuators. So, that you will be having, like in this case it is a main rotor assembly linkages. So, you will be having all these things like the input lever. This is actually carrying the command of the pilot, and then from the input lever the command, as the command comes, then there is a complete kind of a complex linkage system that allows this command in terms of certain displacement or the load to be applied on the main rotor in terms of increasing the RPM of the main rotor or the torque of the main rotor, and then the feedback lever actually sends it back, and accordingly the whole system moves and the pilot takes a decision. So, this is a main rotor linkage system of an helicopter where an electro-hydraulic actuator is used. Similarly, for the tail rotor also the pilot will be having an input lever, and then there are all these valve connection lever, mounting lever. This is just to show you that how from the pilot's position the entire motion transmission through the linkage edge comes, and finally it works on a particular output. So, there is a connecting lever. So, pilot is far away from which this signal or the command comes, and finally that gets attached to the tail rotor system. Okay. Sometimes we also keep a computerized system also, which can take care of something like a fly-by-wire type of a system, which can take care of the system without even the pilot in certain places where it is not so critical. And this is what you see, what is actually happening inside a hydraulic network. You can see that there is a small orifice here, and this block here can actually travel both the ways, and this traveling will actually, I told you that the spool valves movement that will allow the hydraulic fluid to come and apply the force. So, that is taken care of it. So, this is just to show you how actually it would look like such a system. And the overall broad functional diagram, suppose it is an intelligent system where it can take care of on its own, then you will see that it has an automatic flight control system that gives the input to a control and stability augmentation system CSAS, and then there is a LVDT. So, this is a loop that can work on its own. Now, sometimes this loop can be broken by the mechanical pilot input. So, pilot gives the input, and then this input is taken to the main valve system, and then the main valve again applies the power, everything that I told you in a electro-hydraulic system, and a ram position feedback comes here. If there is an error, that error further drives the system. So, these two systems can actually work hand in hand, that is a possibility, or if the pilot mechanical pilot input is 0, even there is no problem, because then the FCS system works on its own. Okay. So, that is what is the kind of a system that drives an intelligent helicopter rotor body. Now, there are some points we have to keep for electro-hydraulic actuator in our mind: the high force density that it has, and then it can be mounted away from the actuation point, that is also a good thing without minimum loss, but there is low efficiency due to some parasitic losses like viscous and pumping loss, clutch cooling, etc. And it is complex system because there are large number of solenoids. These solenoids are used to control the movement of the valves, and leakage of the hydraulic fluid demands continuous maintenance. This is a very important point. If you have to transmit the power, the hydraulic system must be working without any leakage. So, this is of a major concern for such a system. Now, from the electro-hydraulic system, we will go to another type of system which is called electromagnetic system. So, the EM here, EM stands for electromagnetic system. Now, electromagnetic system can be of 4 types: solenoids, DC motors, AC motors, and stepper motors. So, let us look into them quickly. So, this is a solenoid based system, which is essentially a long wear wound in a kind of a helical pattern. So, you can see this wear wound in a helical pattern here. So, you can see the coil systems here, right, something like this. Okay. So, this is what is the coil winding part, and then the coil is carrying a current I in it, and that creates a magnetic field. Now, that magnetic field interacts with these system that is inside and applies a Lorentz force, using which this system can move this plunger system can move back and forth. That is the idea of a solenoid based electromagnetic actuator system. So, naturally the efficiency of such a system depends on the geometry of the system, the electrical configuration, the magnetic permeability. So, for example, the plunger is free to travel in the center of the winding, whether in a linear mode or non-linear. Usually it is loaded with a Belleville spring to keep it linear, and when the coil is driven by an electric current I, a magnetic force is created, and you have to keep in mind that this is actually number of turns per unit length. So, again geometry plays an important role. So, this magnetic force, the Lorentz force, actually forces the plunger to move, and the material property that comes into picture here is the permeability of the steel that is used. The higher the permeability, there will be more forces involved in the system, and the better will be the performance of the system. Also, whenever you are withdrawing the current, it should not remain magnetic, quickly it should become non-magnetic. So, that means the remaining residual magnetism is a problem. So, you have to have as little residual magnetism in the system as possible. Now, to obtain this optimum performance, we really need to design such solenoid systems, which would include the factors like force or torque. I already told you that is general for any actuator, and force versus the stroke. Stroke is how much of distance it can move this actuator system. So, the force versus stroke relationship is very, very important for such a system. Now, one way to design such a system is with the help of typical simple circuit systems for a LRC system. So, this is a inductor, this is L part and inductor, the inductor that is there in terms of these solenoid coils that is there, and then the resistance of the coil R, and then the voltage that you are applying. So, that you get this equation, the so called Maxwell equation, and there these inductance you can further write, keeping this movement of the solenoid in mind. You can write the dl dt as dou L dou x dt. So, that is how you can model electrically the solenoid system. So, this is the further complications that comes in the model, considering the electric flux and considering the different types of resistances that can come into the system, and then on the basis of that complicated analysis further, you should be able to carry out and find out that what is the force that it is going to generate in the system. Now, this is a typical solenoid valve based system, and which is you can see giving a stroke here on this mass, and this mass then can have a to and fro motion in the system. So, that is how you can have this entire system. You can think of it that there is a mechanical system, this part is mechanical and this part is electrical. So, the two systems has to cross talk with each other in order to get an optimal performance of the system. So, that is how the solenoid valve actually have both of these properties inside, and a good combination of the two can ensure a good performance of the system. Now, such a system is also used in another configuration. So, that is called a proof mass actuator. This is used particularly for vibration control. So, what you do here is that, let us say you have a system here which is vibrating to and fro. Okay? You need to control this vibration. So, you have these proof mass here, and you have these electromagnetic coils and attached to the spring and a damper, and you are applying a voltage V. Now, this by applying the voltage, by controlling the polarity, you can create either a north or south pole in a manner that it can either get attracted towards these systems or repelled from this system. So, that you can actually generate a vibration in this system. And if you get a vibration in this system, then if this vibration and this force vibration are in opposite phase, they can basically control each other. So, this is like the similar electrical circuit here, that is having only one important difference, that you are getting a back EMF because of the vibration, the velocity of the proof mass actuator is generating a back EMF, which is working against the voltage, and the governing mechanical equation of the system is having this actuation force involved with it. Now, both the things together, you can actually represent them in the frequency domain by using Laplace transformation. So, this is where you have to use a Laplace transformation, so that you can actually get these equations in a kind of a algebraic form, and then you get two equations. Basically, one equation you are going to get from the system because of the motion of the system. So, that is one, and the other equation you can actually convert. So, this is the other equation, which is for the electrical point of view, and you can add these two equations together in order to get the final transfer function of the system. So, the way it works, there is another way it can work is like you add this. So, this is a primary system vibrating, you add a secondary system to it, and which is this kind of a electromagnetic actuation system, and by controlling this stiffness, one can show that it can actually tune itself to the excitation frequency omega, and such that you can get a 0 vibration response x1. So, you can get a relationship between x2 and x1 with the help of the equations of motions of the two systems, and you can convert them in the frequency domain, and then you can get the response of x2 with respect to x1. And not only that, once you get this x2 with respect to x1, you can actually put it back to the first equation that we have, and through that you can show that at the natural frequency of the second, the mass. So, omega m, so let us say we call it as omega m2, if it equals to omega, then you can show that x1 will tend to be 0, which is what is our intention in terms of the design of such a tuned mass system. Now, this is where now let us close this discussion, and in the next lecture we will talk about smart material based actuators, slightly more advanced actuator system. Thank you.